Okay. Okay, so like I was saying, today we're gonna present chapter 4 of the Fundamentals of Data Visualization book by Klaus Wilke. And my name is Gabby, and I'm going to present, like I mentioned, chapter 4 and 5 today. So chapter 4 is about color scales, and this is a very, I think, fun topic to cover, and I think it's been covered a lot in different packages, and it depends on if you're using R or Python, etc. But still, it's one of my favorite topics to discuss, and one of my favorite topics or things to tinker with whenever I am creating plots or graphs. I think color, I don't know, it's just so much fun. So today what we're going to do is learn how to use color to distinguish groups of data from each other, how to use color to represent data values, and how to use color to highlight certain values or certain categories. So let's start with thinking how to use color as a tool to distinguish something from something else. So those are called qualitative color scales. So here what we do is we use color to distinguish items or groups that are not necessarily ordered. So these are, at least in previous chapters, we saw the concept of factors. So I think that that is exactly what we have here. Whenever we have categories or factors, this is the best way to represent them. And again, there is no order in them. So it's not like one is less than another one or something like that. Another characteristic that qualitative color scales have are finite, or it has a finite set of distinct but equivalent colors, which means that each one of the colors, like you see here in these examples, is that one color is going to be different from the other one, but each color has to represent the same thing. So for example, if we're talking about factors, each one is one single factor. It's not like blue is going to be two factors merged together or something. That won't be okay with this. And the other thing is that they are distinctive enough so that one of them is not standing out. And also they're not very similar. So if we have blues, those blues have to be as different from each other as possible. So we can have, yeah, like I said, it's not all blues, but if we can have two blues there, or two reds or two oranges, they have to be further apart from each other and as different as possible. And it's important to note that colors should not create the impression of order here. So there have to be just to distinguish different categories, different factors. So here we have 3 examples. One of them, these are like from different color palettes. They are all, I'm not sure if they're all from Color Brewer, but what you can see here is exactly that. Like each one of the colors is distinct from the next. And if we see an example in a graph, here you can see, for example, the percent population growth. So on the x-axis, we have population growth from 2000 to 2010. And on the y-axis, we have different states, US states. So here, when you color each group of bars, what they're representing are categories. In this example are regions. So the West, South, Midwest, or Northeast regions. So when you see these graphs, you can rather rapidly organize them in your mind and say, okay, so if I'm comparing all the green ones, those are all from the Midwest. So that is the category that green is representing, right? We can also use color to represent data values. So in this case, the color is used to represent, for example, incomes, temperature, speed, and you can sort of bin them in bins, right, in categories to represent values from 0 to 5, 0 to 10, or something like that. And then each category represents that bin. These are called sequential color scales. And it's called sequential because each sequence is going to indicate which values are larger or smaller, which color scale needs to be, which values are larger or smaller, like what you see here in this blue or different hues of blue in this first example, the color scale also needs to be perceived to vary uniformly across the range. So that means that each one of these different shades of blue or the color that you chose, they have to vary uniformly, meaning that the amount of values that are in each one is the same. That's super helpful for the viewer or for the person that is reading or analyzing the graph, so that they understand that each one of those steps represents the same amount. So that means that how distant two specific values are from each other is exactly the same. It may be based on a single hue, like for example here with the blues, that goes from dark blue to light blue, or it can represent multiple hues, like the one here from a color palette called Heat. And this is going like with multiple hues, going from light yellow all the way up to dark red. So it goes from, it's kind of like in the order, it has to be like in a natural order, like what you see the gradient going in the rainbow that goes from green, goes from yellow, sorry, to oranges and then to red. That is the best way to do these color gradients. But there are others that are already made, like the Viridis color palette. There are others that are called the Mako color palette. And I don't remember what's the other one called. But those color scales are already made, are pre-made for you, and a bunch of packages already have them, at least in R, which is the one that I use the most. They already exist. So it's easy to just follow those pre-made sequential color palettes. And in this case with Viridis, it goes from yellow, from all the way up to green, and then blue, and then it ends in purple. Like I said, there is like a sequence following like rainbow colors. In this case, we have an example of a choropleth where we have a map showing the annual median income within each county in Texas. So you can see that the sequential color palette goes from a very light blue all the way to dark blue. And this goes from the very low, the very light blue shades represent a very low value, and the darker shades represent a higher, in this case, median income, right? Higher values. So then when you display that in a map, it's super easy to distinguish differences between each category. Okay, we also have diverging color scales, which are essentially to highlight midpoints, or these color scales are used to highlight midpoints, where a midpoint, it's going to mean something, or it's going to have an importance in this case. So it's like I was saying, the midpoint is going to be in between two sequential scales. And the midpoint is going to have like a different color. It's going to have either lighter, usually it's the lighter color, so that it goes from very dark all the way to light. And then again, it increases to a different darker color. So this is used to visualize deviation of data values in one of two directions relative to a neutral midpoint, like when you see positive and negative values and the center would be 0. It's also used to balance or it also has to be balanced to indicate progression of colors in either direction in either direction. So in this case, the magnitude or in either direction, it has to be the same. So it has to be balanced. So in these examples here, you can see that the midpoint is going to be super, super light, and then it starts to increase in darkness all the way up to one side versus the other one. In this example, we also have a choropleth where we are showing the percentage of people identifying as white in Texas counties. So here, what they're using as a midpoint is 50%. And that is a meaningful midpoint value because it shows that that is exactly where the author wants the viewer to, or the reader to focus their attention. And then it's going to be super easy to say lower values or values that are lower from 50% are going to be in this like brownish scale. And then all the higher values all the way up to 100% are going to be increasing in color in this like teal color, if you will, or aqua. I don't really sure what color that is. Then we can also use color as a tool to highlight a specific category or value. And the way you do this is by emphasizing certain elements in your figure, and those elements are highlighted in this very dark color to strengthen the story that you want to show, or to highlight certain points in comparison to the rest. So this color set or color sets that are used to highlight certain points have certain colors that are vividly or that vividly stand out against the rest. So if you can see this 3 color palettes that we have here in the bottom, you can see that we have 3 colors that are used as highlights, and those are like darker in hue or have a darker hue compared to the rest, which are very light. These color palettes are usually called accent color scales. And you're gonna see, like, for example, here, it's color brewer accent, grays with accent. So every time you see that word accent, it's because it's gonna have like this scale. And the baseline colors must not compete for attention, but instead support the accent color. So you can also see that the baseline colors, which are these initial 4 colors, really do not stand out in comparison to the rest. And when you see it in a graph, you really see that they help to highlight the accent color or colors that you wanna show. So for example, here in this graph, you see that all the colors are muted in a way, except for the Texas and Louisiana bars. And that is because the author wants to highlight, for whatever reason, the values of those 2 states. This is another example too that we have here where in doubt, just use the baseline colors as gray. Just gray them out, different shades of gray, and then your highlight color becomes red, blue, orange, whichever color you want to use. Okay, so that is everything for chapter 4. Doing like an assessment of this chapter, I think that it's, again, quick to get the information. It's very succinct, and I appreciate that a lot. But I think that the thing that it's missing is the how to handle color blindness in your color palettes. I would have liked to see a specific chapter on that, because it's very common to find colorblind people, obviously in the audience if you're presenting something in a conference or something like that, or looking at your graphs. So for that, I just want to show you something real quick. There is this website. I'm not sure if everybody's familiar with it, but it's called Color Brewer. And here what you can see is this is made specifically for maps because it's color advice for cartography. But in reality, you can use all the colors and all the palettes that they are giving you here for graphs too. So all you have to do is like copy the hex colors, for example, and then you can create your own color palettes in R or Python or whatever language you're using. So if you start here saying how many classes you have, so let's say if I have 5 classes, and then I specify if I want a sequential, a diverging, or a qualitative color palette, which are the ones that we just saw in chapter 4. And then you can also mark this box that says colorblind safe. And that is going to show you exclusively color palettes that are going to be colorblind safe. So for example, if I go to diverging with 5 different classes, and then so it shows me 1, 2, 3, 4, 5, 6, 7, 8, 9. But when I tick this box and say colorblind safe, it only shows 6. So the final three, these ones are not going to be colorblind safe or friendly. So I think that that is important to consider, and at least in R, there are a ton of packages that also deal with how to deal with colorblind friendly colors. So I hope that that was oh yeah, Coolers is also very cool. So Amir shared this website. Yeah, so this is a very cool website. It's called Coolers because it's cool. And it has like different here. So you have to sometimes create a username with this one. The only thing that I do is explore trending palettes. That's the only one I've used without signing up. And here you can have previously made color palettes. And then you can, if you click here, I think it's open palette, and then you can copy the hex values, for example, and it's going to show you two similar palettes. And then you can use, for example, all of these colors could be like your color base, and then you go and find accent colors to just to create your own color palette. So thank you, Amir, for that. That one's also super cool super cool website to use. Okay, so now let's move to chapter 5. This chapter is the fastest one of all, and it's the only thing that shows this chapter is a directory of visualizations. So essentially what we do, or what we're going to do here, is have a quick visual overview of several plots that are commonly used. So it's divided by these categories that are going to be amounts, distributions, proportions, XY relationships, geospatial data, and uncertainty. So the thing that I did with this chapter was I only pasted, because information that the author provides is not a lot, but I think the way that we can use this going forward is just having, if we're clicking any of these subtitles, we will have access to just the graphs and the name of the graph. And then we can go in R or Python or whichever language we're using, and then just look for how to create strip charts in R. So I think that this is, what I thought was like to have this as a quick reference whenever we're creating plots or something, instead of having the book and then doing this, like going through this whole chapter, right? I thought that would be rather, I don't know, useful for us. Okay, so here, what we can see here, to represent amounts, we have bar plots that can be horizontal or vertical, but we also have dots. So the end of each one of these bars is going to be represented by the dot. So that's like the maximum value for each one of the categories. But when you have grouped values that are not necessarily just one specific category, then you have the option to do grouped bars, again, horizontal or vertical, and stacked bars. We also have heat maps, which this is one of my favorite graphs to do. And if I can just do a heat map for anything or whatever, then believe me, that's what I'm going to do. I just think they're so fun to do. But anyway, to represent distributions, we have different examples. Usually the ones that we use are histograms or density plots if we have just one distribution to show. Then we also have cumulative density. I think these are called, there's a name to represent them other than cumulative density, but I forgot. And this is only showing how the values are accumulating. So it's different than showing the density plot itself. And then the quantile plot, what it shows is just how the distribution varies along an XY line trend that is equal to 1. And then you can, with contel plot, you can see deviations from the normal distribution. So whenever you have a bunch of points centered or gathered in the center, and then the tails are still on the line, but very few data on the tails, then that is more likely a distribution that is normally distributed. But then when we have several distributions that we want to compare, then what do we do? So there are box plots, violin plots. There's also, I think, half violin. We also have strip charts, Thena plots, stacked histograms, overlapping densities, and rich line plots. So out of all of this, the ones that I think are the best to represent grouped distributions that we want to compare are going to be the Thena plots and the rich line plots. Some people like violins too for this, but to me, what violins represent is like they are, so the same thing that you see on the right side is exactly the same on the left side. So to me, that's just duplicating the same thing. So I don't really see the point in that. But I prefer violins over box plots because in order to understand a box plot, you have to know what a box plot is. So it's not as intuitive as, for example, a Thena plot or a rich line plot. But again, box plots are very used, especially in scientific journals. The author does highlight the fact that stacked histograms should not be used as much. Okay, they should not be used as much because, again, sometimes you can hide certain parts of the distribution. So instead of using stacked histograms, it's better to use overlapping densities or rich line plots. So in my experience, these rich line plots, well, I use R, so that's my language. So what you can do is like separate them as much as possible so that there's very little overlapping. And that way you can say like, so this is going to be my first group, my second group, my third group, and there's very little overlap so that you can still compare across them, but not necessarily have the shading of this distribution affect what you're seeing in the back of the other one, right? So that's one thing. The other one is with overlapping densities. Again, you have to choose your colors very, very carefully. And these three things have to be as see-through as possible so that you can actually see what's happening in the distribution that's in the back of the first one. So I think that that's the only key. The difference between Thena plots and strip charts is that strip charts are going to represent so how many points are per distribution, so how many values you have per group. But the Thena plots goes a little bit further, and they're like a violin but with plots because they're using the density of your points to jitter them and to separate them. So you see that there's a bunch of them here as opposed to the ones that are in the top and bottom of that group at least. So then you're showing a bit more information. So I'm a big fan of Thena plots for that reason. Okay. The other way of showing relationship between bars is with proportions. So when you have proportions, the ones that, or the usual suspects are pie charts, bars, and then if you have multiple, you have grouped bars, or stacked density. So I think that there is an occasion for each one. So there are people that don't like pie charts. I'm not sure what your opinions are on them. I think they have a place and an audience for them, but it's usually like, because it only represents one dimension, I'm not really a fan of them either. And then when you want to compare multiple groups, what happens is that you are using a lot of space to represent comparison between groups. And then sometimes it's intuitive to see it, but I think that it's best if you represent it with, for example, grouped bars or stacked densities. I think that that's sometimes better. The other three examples of graphs that the author gives us for proportions are mosaic plots, tree maps, and parallel sets. These are also called something like Dansky or Stanky.
Thank
Yeah, that one, Stanky, something like that. I'm not really sure. Ashley, can you put the name in the chat? Yeah, Stanky, that's the thing. Yeah, Stanky. So my personal opinion, I don't like this three ones, either of them. But again, this is just my personal opinion. The author is not saying anything about that. I don't like them. The reason is because in the mosaic plot, you have to compare areas. And can we really do that intuitively? Sometimes if you have very few groups, it is intuitive, but then as you add more, the thing complicates too much. Same thing with tree map. You need to understand the graph in order to understand. I don't know that I really don't like that. And then these things, if you have too many ribbons, you lose like the order. Like where is this going? Like it's crazy. Anybody has an opinion on that? Ashley, do you have an opinion on that?
Yeah, I mean, part of the reason why pie charts are often discouraged is because we as a species tend to have
Mm-hmm.
trouble differentiating the size of areas.
Mm-hmm.
So, like you said, the mosaic plots and the tree maps kind of don't work with that. I find they can be helpful if you have like a ton of things that fit into some
Mm-hmm.
categories. Like I think one of my favorite examples of I think it's a mosaic plot is like it's like a data visualization of like the Pokédex from like Pokemon,
Mm-hmm.
and it just
Mm-hmm.
like you can see by the colors like how many like what proportion of all of the Pokemon are like water type or grass type or whatever. And like I think that's a good use of it. Personally, I really like stacked bar charts.
Mm-hmm.
Um, I've used them like in public talks to talk
Mm-hmm.
about how the proportion of like different types of animals differ depending on time period generally.
Mm-hmm.
And people seem to people seem to understand what's going on when you show it to them that way. So that's I think that's helpful.
Mm-hmm. Yeah, and I think that stacked bars are exactly like what pie charts are showing, but you're using the space more efficiently. So I think I agree with you. Stacked bars
Totally.
have, yeah, have their place. Another chart that is not shown here, but it's also useful to show proportions, is donut charts, which are essentially you have one of these bars and then you put it as a donut. So with like the middle is like taken out of it, so it looks like a donut. So there are a few graphs that are not shown here, and I think that that is something that yeah, that you if you come into contact with other types of graphs that are not in this directory visualizations, I mean, you're gonna have to just, I don't know, see if they're showing proportions, distributions, or something like that. So I've seen those donuts that it's a little bit like having pie charts, so they again have their time or the place. The other thing I don't like about pie charts is that they show just one variable. I don't know if I mentioned that or not. So pie charts are just very unidimensional. And as scientists, usually what we want to show is relationship between variables. So that you can see with all the other ones. So stacked bars, for example, you're showing exactly in different groups the relationship between X and Y. So how much of X you have per group and the relationship with Y too. So I that's why I like them better too. So then we have the XY relationship. So these are some of the most common graphs that you're gonna encounter. So scatter plots, for example, I think that's like the way to start everything is with a scatter plot to sort of like explore what your data looks like. We also have bubble charts where the size of each bubble is going to represent a third quantitative variable. So then that's how you show three variables or the relationship between three variables in one plot. Then we have paired scatter plots. This is to show like correlation or regression, some things like that. And then there's also slope graphs. I've also seen them as dumbbell plots, I think. And then if you have too many points, then the scatter plot becomes like a cloud of points that you cannot really see anything inside of that. So then the author recommends that when that happens, then go to density contours, 2D bins or hex bins. The hex bins is essentially a 2D bin too, it's just that represented with hexagons. So then you're creating like with colors, you're showing the density of points. So that I think that helps a little bit to clean a little bit those scatter plots that look just too cluttered or crowded. Then we also have correlograms. I've seen this with correlation. So if you're going to see the correlation between two variables, x and y, and then you can show by color, or you can also put the little number here, you can say that this group here, compared to this one, like these two things, like the correlation between those two is, let's say, 0.4. And then as it gets darker, let's say if this went from green to blue, as it gets darker, then it's going closer to 1. Or as it gets lighter, it's going to yellow, for example, or something. It's going to negative values, or it depends if you want to do it from 0 to 1 or from -1 to 1. So that's how I've seen the correlogram used. And then we have line graphs, which are just points joined by a line. And then we have connected scatter plot, which is showing where something starts and then it goes and the movements that shows. So this can be, for example, if we're talking about human mobility data, then we can show that humans start here and then they move to this other area. If this is showing X and Y, what do you call those things? Coordinates, X and Y coordinates, latitude and longitude, then you can show the direction and where it begins, the movement of people, and then where it ends. Like, for example, if you're talking about a mall, for example, or a store, like where is the direction of the tendency of the direction of how people move inside that store or inside an area or something like that. Then we also have smooth line graphs, which this shows the association between two variables again, that you did a model, for example, a regression, or you did a GLM or something like that. And then this is showing the tendency of the association between these two lines based on the analysis that you did. And usually you show also like the scatter plot with all the data that you have in the background. Okay, then we have geospatial data. This is very easy. You can have a map, and then if every color or the shade of colors is going to represent a quantity or a category, then that's called choropleth. You can also have cartograms where you can inflate and add a third quantitative variable, where if you're showing here, for example, the density, population density, then you're going to see that the more inflated states are going to have a larger population density value, and then the skinny ones are going to be less densely populated. I've seen this with like the what do you call that thing? The human carbon footprint, or the human footprint. I've seen that done with this thing, but it's also like with poverty, level of poverty. Think of any quantitative variable that you want to show like the difference in magnitude between different states or different countries or different regions. And then we also have cartogram heat maps, which this essentially what it's showing is that it's like a simplification of a map where you're going to put the order of these little squares corresponding to more or less the order of these, in this case, states. But this could also be like countries. And then this is going to show also, like, for example, the different shades are going to be like the population density, or they're going to show categories of something. So then you are comparing them, but it's like a simplification of a map. I love this cartogram heat maps, by the way. And then if you want to show uncertainty in your values, then the usual suspects are going to be error bars, which can be with a point, and then the maximum value of that group is going to be where the point lays, unless it shows like median or mean or something like that. And then the error bars are going to show either standard deviation, error, standard error. It can also show variance, or it can, and you have to say if this is one standard deviation from here, or two standard deviations, or what. And then error bars are going to show the same, also like 95% confidence intervals. That's another way of showing this. The other thing is with graded error bars, you can actually show one standard deviation, then the other shade is going to show the two standard deviations, and then the third one is going to show three standard deviations. So these graded error bars are super cool for that too. There are also other ones like quantile dot plots, half eyes, which is the same thing as violin, but it has like the error in the middle, and then confidence strips with the darker it gets, it's because that's the center, and then the way they vary, again, standard deviation, standard error, all of those, it's gonna expand to the side. We also have for, again, models, if you have like your model shown with the tendency that your data is showing and you have that on a line, and then you add 95% confident intervals, for example, shown with this band. And it's usually a little lighter so that you can see the line and the contrast with the shaded band. You can also have a graded confidence band, and that is if you want to show, for example, 95, 90%, and different levels, and 80% of confidence levels. That's usually how you can show that too. And sometimes instead of showing the shaded band with your confidence intervals, sometimes what you want to do is different fitted draws. I've seen this, like, for example, when you do a Bayesian analysis and you want to see how your distributions, how all your iterations for a distribution, if you do like 20,000, for example, then you stack them all together. Each line is like a iteration, and then you have that on top of all of them, and then you have like your 20,000 draws here. That's one way that I've seen those guys used to show uncertainty. So I think that is this chapter. 44 minutes to show two chapters. So I think that was that was a good idea to merge these two chapters. So now I'm gonna just open the mic. If anybody has any like opinions or questions, or I don't know, something that they wanna discuss. Again, this showed my full name. It should just show Gabby, but this thing is just giving all my information to the work.
It all docs you now.
Yeah. Thank you, Amir. It's all good. Thanks for showing up.
I was trying to find, I feel like there's this one graph that like haunts me from like 10 years ago that I can't find now, but I think it was similar to like a slope graph or slopegram, whatever they're called. And it was like, if I remember correctly, it was showing like differences in limb proportions.
Oh.
And it was just, I hated it so much. I found it so unintuitive. And if I could find it, I was going to show it to everybody, but I don't know if I will be able to.
Yeah, that's me with Sunkeys. I honestly don't, unless there are very few categories that you're comparing, then it makes sense. But when you have like a ton, I'm like, how am I gonna follow all the ribbons? Like, I hate them. But I think some people just love them, and I've only seen them used well in a publication once, and then I'm like 80% convinced it was a good idea. But
Yeah,
yeah,
I think like I find like Sankey diagrams, if you show when they're showing like international trade, for example,
Mm-hmm.
Like I find that's a pretty good use of them. If it's like big categories where you've got like agriculture products and
Mm-hmm.
I don't know, other stuff that
Mm-hmm.
people trade. Because you
Metals,
can
yeah,
find,
flowers,
yeah,
yeah.
metals, yeah, um, like textiles.
Mm-hmm.
You can like find your thing and you can trace it across and see like kind of the steps of how things are moving across the globe, which I find helpful.
Yeah, and I
I,
guess it's comparing like a one moment to the next. Like if you're comparing one decade to the next, like when something
mhm.
started and where it ends, I guess yes, that sort of makes sense too. But I don't know. I still need to. Hmm.
They take a
I don't
lot
know.
of they take a lot of cognitive resources to process. You need to be really invested in finding out what you want to know.
Exactly. So I don't. That's why they're not my favorite, but I think maybe I haven't really seen a good example of them. So then maybe that's going to be my mission now. I'm going to try to find the best examples of sand keys to show this is how they should be done or used. But anyway, yeah. Okay, so before we end, I just want to highlight the fact that I don't think we have anyone for next year. But let
Next
me see
week.
if I can next year, next week, if only next year. Next week, let me see. Claim a chapter. Okay. Yeah, we don't have anyone for next week. So if anybody's interested, oh, Josh has chapter 7. Um, but Josh is not here. I'm gonna make a comment or I'm gonna post something on Slack and see if he wants to present next week so that we can do 6 and 7 together. Because he's exactly yeah, he signed up for 7. But I'll see if he wants to do 6 and 7. And then we also don't have anybody for the following week, which would be um, chapter 8 and 9. So if anybody's interested, just go ahead and sign up for those. If not, I'll do them because that's why I'm the what's the word? No, it's not coordinator, it's the facilitator, I think it is. Yeah, so cohort leader or whatever. So yeah. Anyway, if anybody has any other comments, we can discuss those. If not, then we will meet next week, where we will continue with chapters 6 and 7. All right, you guys, thanks for